All right, strap in, because today we're going deep on something pretty wild.
Oh, yeah.
Quantum recurrent neural networks, or QRNNs for short.
Okay, I'm listening.
It's basically like, imagine the power of quantum mechanics, but harnessed by artificial intelligence.
Whoa, that's a pretty powerful combo.
It is, and that's the future that Jürgen Schneppert lays out in his essay.
Interesting.
QRNNs, Quantum Recurrent Neural Networks für fortschrittliche KI. And trust me, it's a fascinating read.
You've got my attention now.
So what I find really interesting is that Schneppert isn't just, theorizing. He's talking about real-world applications that could completely change everything.
You're like, what?
We're talking about things like cracking codes that we thought were unbreakable.
Right.
Or even understanding the universe at a whole new level.
I mean, that's pretty ambitious.
It is, but before we get too far ahead of ourselves, I think we need like a little bit of a quantum mechanics 101.
Yeah, you're right.
Just to make sure we're all on the same page.
Totally agree. So let's start with a few key concepts.
Okay, sounds good.
First up is superposition.
Superposition, okay.
So imagine a qubit, which is basically the quantum version of a bit rate.
Yeah.
And it can be both a 0 and a 1 at the same time.
Wait, so it's both at the same time?
Yeah, it's kind of like, think of a coin spinning in the air.
Okay.
Before it lands, it's both heads and tails, right?
Right.
That's superposition, and that lets QRNNs explore tons of possibilities all at once.
I see. So it's not like one or the other. It's like it's doing both.
Exactly. And that makes them super efficient for certain problems.
So instead of like going through each calculation one by one, it can kind of tackle them all at the same time?
Yeah, it's like a massive speed boost.
Wow.
And then there's entanglement.
Okay, entanglement. This is where it gets kind of freaky, right?
Yeah, a little bit.
I've heard about this.
It's where you have these two qubits that become linked, even if they're super far apart, and any change to one instantly affects the other.
So like you're talking to each other somehow.
Yeah, it's like they have this secret communication channel,
Whoa.
even across huge distances.
Okay, that is seriously mind-blowing.
It is a very strange concept.
So how does all of this like quantum stuff actually translate into a neural network?
Ew, that's a good question.
Like I get the quantum mechanics part, but how do you actually build a network out of it?
Yeah, before we jump into that, let's do a super quick RNN refresher.
All right, RNNs, recurrent neural networks.
Exactly.
Okay.
So those are designed to analyze sequential data.
Like sequences of information.
Yeah, think about things like stock prices or weather patterns.
Gotcha.
Even sentences.
Sentences, okay, yeah.
Yeah, and their power really comes from remembering information from previous steps.
Okay, so it's kind of like an AI that can like read a book and remember everything it's seen.
Yeah, pretty much.
That's amazing.
It is, but traditional RNNs, they have some limitations.
Okay.
One of them is, it's called the vanishing gradient problem.
Vanishing gradient problem.
Yeah, imagine like playing telephone.
Oh.
As the message goes around the circle, it gets weaker, right?
Right, yeah, it gets all garbled.
Exactly. In RNNs, it means they have trouble remembering information from those earlier steps.
Ah, so like the further back you go, the fuzzier it gets.
Yeah, like trying to remember the first line of a book after you finished it.
Exactly.
Okay,
Yeah.
I get it.
That's where QRNNs come in.
Okay, so how do they fix that?
Well, Schneppett's argument is that by using qubits instead of classical bits
Okay.
with their superposition and entanglement powers,
Yeah.
QRNNs can maintain a much clearer memory.
Oh, so it's like their memory is just way better.
Yeah, they can process information in parallel and recognize complex patterns.
Well, that traditional RNNs might miss.
Exactly.
So instead of just like a string of ones and zeros, it's like this whole quantum state that can hold way more information.
Yeah, and make connections that traditional networks just can't.
Okay, no, that is super interesting.
It just like traditional neural networks use logic gates to process information.
QRNNs use quantum gates.
Quantum gates, okay.
So think of it like building with Legos.
Right.
Classical computers, they only have limited block shapes.
Right.
But quantum gates give QRNNs way more building options.
I see.
Leading to more complex and powerful structures.
Okay, so we've got these quantum-powered RNNs.
Right.
That can theoretically process information in ways that we never thought possible before.
Yeah.
But I'm dying to know, what could this actually look like in the real world? Like, what kind of real-world applications does Schneppert actually envision?
Yeah, that's the exciting part. So Schnepp actually gets into some pretty specific examples in the essay.
Okay, like what?
Well, for instance, he talks about time series analysis.
Time series analysis.
Imagine trying to analyze data from like millions of sensors in a smart city.
Wow.
All happening in real time.
That's a lot of data.
It is. A QRNN could potentially predict traffic jams before they even start.
Really?
Or optimize energy consumption with crazy accuracy.
That's like having a crystal ball for a whole city.
Yeah, pretty much.
That's incredible. But, I mean, wouldn't analyzing that much data in real time be overwhelming, even for, like, a super advanced QRNN?
It's a good question, and Schnepp acknowledges that there are current limitations with quantum computers.
Right.
But he believes that as the technology gets better, QRNNs will be able to handle those massive data sets.
I mean, it makes sense. We're still pretty early in the game with quantum computing. Right?
Exactly. It's like we have this amazing race car.
Okay.
But we're still figuring out how to build a racetrack that can handle its speed.
I like that analogy.
So let's switch gears a little bit.
Okay.
And talk about another area where this could have a huge impact.
All right. I'm ready to go.
Cryptography and security.
Ooh, okay.
Imagine codes that are so complex that even the best hackers in the world can't crack them.
That would be amazing.
Right. Schnepp suggests that QRNNs could be the key to creating these ultra-secure systems.
So this is like a quantum arms race.
Kind of. We need QRNNs to defend ourselves against the potential threats of quantum computers themselves.
Oh, wow. So it's like we're building a shield.
Yeah.
To protect us from the weapons that we're also building.
Exactly. It's a little bit ironic, but that's the reality.
Did Schnepp seem concerned at all about the potential for misuse?
He does acknowledge the ethical considerations,
Mm-hmm.
but he focuses more on the positive applications.
Okay.
For example, he talks about how QRNNs could totally revolutionize scientific simulations.
Scientific simulations?
Like, imagine being able to analyze complex signals from space.
Yeah.
To understand the origins of the universe.
That's mind-blowing.
Or simulating molecular interactions to accelerate drug discovery.
Wow. That would change medicine forever.
Absolutely. These are areas where traditional AI just hits a wall.
Yeah, I can see that.
It can't handle that level of complexity.
Okay, so this is all very exciting, but let's be real for a second.
Sure.
Schnepp is obviously super enthusiastic about the potential, but he also talks about the challenges.
Wow, absolutely.
It's not like we can just snap our fingers and have working QRNNs tomorrow.
It's not that easy.
What are some of the hurdles that he mentions?
Well, one of the biggest ones is the hardware.
The hardware. Okay.
We just don't have enough qubits right now.
Qubits, right. Those are the building blocks of quantum computers.
Yeah, to build really complex QRNNs.
I see.
And the qubits that we do have are really sensitive to noise.
Noise like interference.
Yeah, and that can cause errors.
Right. So it's like we have this amazing recipe for a gourmet meal, but our kitchen is missing some key appliances.
That's a great way to put it.
Yeah.
And beyond the hardware limitations, there's also the challenge of developing the algorithms that can actually harness the power of QRNNs.
So it's not just about building better quantum computers.
No.
We also need a whole new way of thinking about programming.
Right.
And training these networks.
It's a whole new paradigm.
It sounds incredibly complex.
It is. And then there's another layer of complexity on top of that.
Really?
Remember that spooky action at a distance we talked about?
Yeah.
Entanglement.
Yeah.
Well, maintaining that delicate state of entanglement is super tricky.
Okay, why is that?
It's susceptible to something called decoherence.
Decoherence?
Where the entanglement basically breaks down because of environmental noise.
So it's like you're trying to balance a spinning plate on a stick while walking a tightrope.
Yeah, one little wobble and the whole thing falls apart.
Wow, that's a good analogy.
So developing robust error correction techniques is crucial for building reliable QRNNs.
Okay, so it's a big challenge.
Yeah, it's a major focus of ongoing research.
I can imagine. So we've got these hardware and algorithmic challenges.
Right.
Plus this whole delicate nature of entanglement to deal with. Where does that leave us in terms of comparing QRNNs to like our current AI models?
That's a great question.
Is it even a fair comparison at this point?
Well, it's tough to say. I mean, on the one hand, you've got QRNNs with this massive potential for speed.
Right.
And they might even be able to like spot patterns that classical AI would completely miss.
Totally.
But as we've been talking about, they are kind of held back by those real world limitations right now.
So it's like comparing a thoroughbred racehorse that's still in training.
Oh, yeah.
To a reliable but maybe a bit slower workhorse.
I like that.
The thoroughbred has all this potential to win big.
Right.
But it's not quite ready for the Kentucky Derby just yet.
Exactly. And then you've got those trusty classical AI models.
Yeah.
They're here. They work, and they've already proven themselves in so many ways.
For getting the job done.
They are. But they do struggle with really complex tasks.
Yeah.
And training them on massive data sets, it takes a ton of energy.
It's just a resource-intensive process.
It is. So for now, classical AI is still that reliable workhorse. Mm-hmm. But QRNNs are this exciting new prospect with the potential to really shake things up.
If we can figure out how to,
Yeah, unleash their full power.
Exactly.
Yeah.
Now, what I found really interesting about Schneppat's essay is that he doesn't just focus on the technical details. Mm-hmm. He actually grapples with this bigger picture question.
Which is?
What would a world powered by QRNNs actually look like?
Right, and that's the really thought-provoking part.
It is. I mean, he paints this picture of personalized medicine, traffic flowing smoothly through these super smart cities.
It's a very optimistic vision.
And scientific breakthroughs happening like lightning fast.
It's almost utopian in a way.
Yeah. But we also have to remember that technology is a tool.
Of course.
It can be used for good or bad.
Absolutely.
As QRNNs become more powerful, we need to start asking some tough questions.
Like what kind of questions?
About their impact on society. Who controls this technology? Who benefits from it?
Those are important questions.
Could it actually widen the gap between the haves and have-nots?
Right. Those are all things we really need to consider carefully.
Absolutely. Yeah. Now, Schneppat himself. Yeah. He doesn't shy away from these ethical considerations.
No, he doesn't.
He really stresses the need for thoughtful regulation and guidelines.
To make sure that...
To ensure that QRNNs benefit everyone.
Right, not just a select few.
Exactly. It feels like we're at a crossroads with one path leading to incredible progress and the other to a world where technology actually makes existing problems even worse.
It's a powerful image.
It is. And the choices that we make now, they're going to determine which path we take.
I agree with that.
We need to have open and honest conversations about the potential of QRNNs and involve not just the experts, but the public as well.
Absolutely. Everyone needs to be a part of this conversation.
Okay, so we've just scratched the surface of this topic today.
We have, but it's a fascinating one.
But one thing is clear.
What's that?
QRNNs have the power to be truly revolutionary.
I agree.
Not just for technology, but for how we understand ourselves and the universe.
It's a really profound idea.
It is. Now, as we wrap up this deep dive into QRNNs, what's the one key takeaway you want to leave our listeners with?
I think the most important thing is to just stay informed and engaged.
Okay.
This field is moving so quickly.
It is.
And we all need to be prepared for the changes that are coming.
So pay attention. Do your research.
Exactly.
And who knows?
Yeah.
Maybe QRNNs will help us unlock some of the universe's biggest mysteries.
It's possible.
Leading to breakthroughs that we can't even imagine today.
And that's what makes it so exciting.
Schneppat's essay definitely gives us a lot to think about.
It does. And, if this deep dive has piqued your interest, I encourage you to go and learn more about QRNNs and the work of Jorgo Schneppat.
Absolutely. He's a brilliant mind.
He is. And who knows, maybe you'll be the one to make the next groundbreaking discovery in this amazing field.
That's a great thought to end on. So thank you so much for joining me on this deep dive into QRNNs.
It was a pleasure being here.
It's been a fascinating conversation. And to all of our listeners out there, keep exploring, keep questioning, and we'll see you on the next deep dive.